Hello. First question. How many geologists in the room? Geologists. There's one there. No colleagues? No? Oh, sad. So welcome to my talk, where we will jump a little bit on asteroids and a bit of geology, geophysics, impact processes, and also a little bit on optical properties. Today, I decided to present an experiment with it on terrestrial rocks, dunite, which somehow reflect the composition of rocky asteroids. And by experimentation, we could darken this rock with iron sulfides. Now the question is, why did we do that? The first aspect of this work are these two little fragments of meteorites that fell in 2013, but the Chelyabinsk meteorite that fell in Chelyabinsk region. And when we gathered these samples, we saw that one of these samples is especially light optically, like with eyes, but also with reflectance spectra. And the other type of fragments are actually darkened. With the important particularity that they have the exact same composition. I mean, there is the same amount of silicate, same amount of metals, and same amount of iron sulfide inside. One is dark and one is light. There's also a third lithology that were found on these meteorites, which is the shock melted, which was also dark in appearance, but I will show later what are the difference between dark lithology and shock melted lithology. First, before explaining on the asteroid level, let's just take a look on backscatter electron microscope image of these two fragments. On the left, so we have the light lithology, and on the right, we have the dark lithology. For information, ordinary chondrite, because Chelyabinsk is an ordinary chondrite, they are composed of olivine, pyroxenes, and plagioclase, which are silicates. Olivine and pyroxenes are rich in magnesium rather than iron. And these meteorites are also composed of alloy, of these iron nickel alloys, kamacite, dunite, and also with these iron sulfides, chrolite in this instance. When you take a look at how this material distributes on the left, compared on how they distribute on the right. On the left, all these metallic and iron sulfide elements, like in bright color, like bright white. In the light lithology, they are in the form of grains or clusters of grains in contact with each other or not. But in the dark lithology, all of these iron sulfides and partially the iron nickel alloys, they have spread in between the silicate grains, and which consequently darkens the lithology. At least this is what is believed to be, and which is true. So I've worked a lot to try to understand this process, but it's important for us right now today to understand why it is important. So when we survey the asteroids, the main belt or the near Earth asteroids, there is this classification from the NEO, and first classification, if I remember well, where we have two main groups. There is other groups, but here present only two of them. Two main groups that are characterized by different type of spectra in the near infrared. The S-complex asteroids usually are considered to be the rocky type asteroids, meaning that they are mostly rich in silicates, and they are mostly composed of these ordinary dendrites, like with olivine, pyroxenes, plagioclase, and alloys, and iron sulfides. Then we have the carbonaceous the C-complex asteroids, and these ones mainly host carbonaceous chondrites. When you take an ordinary chondrite in one hand and carbonaceous chondrite in the other hand, most of the time, the carbonaceous chondrite will be dark. Not always, but it will be dark compared to the ordinary chondrite, which will be light. And it is reflected in these reflected spectrum. As you see here, it's in the near infrared. And you see that the light lithology of this ordinary chondrite, Chelyabinsk, shows two typical absorption bands at 1 micron and 2 micron, which is attributed to the silicates. But when you look at the dark lithology, you look that there is absence of these two absorption bands. Although the pyroxenes and olivines, or the wire silicates, are still within the rock. But this darkening just erases this typical profile, the light lithology chondrites. And they can be compared, obviously, to the asteroids. Here, the light lithology has spectra that looks alike to S-complex asteroids, and the dark lithology has spectra that looks like C-complex asteroid or X-complex. That's problematic. It means that it poses one important question when we observe asteroid, is to understand how much of these dark asteroids that are observed from Earth or from space are actually S-complex asteroid that has been darkened from any processes that helps in darkening the lithology. Today, I just focus on the darkening with this iron sulfide. But there is also darkening by space weathering, darkening by shock melting, as I've shown there as well. You see here the dotted lines. It's like shock melted, but you still see a little bit of this absorption bands compared to the complete dark lithology. Here is just an overview of most of the work I've been doing before, mostly with shock physics and shock modeling, which gave me some approximation of the temperature that might be needed to obtain short darkening, and also in what kind of impact we are most likely to produce this kind of pressures. But today, the experiments I am presenting kind of answered other important questions, because there is one question is it only by shock, like by impact between asteroids or not? And to answer this, we created these singular experiments where we have this dunite cube. So dunite is composed of olivine, magnesium olivine mostly. And we filled little drill holes with this trolite that we have synthesized in the laboratory. We take these cubes, we put them in the oven at 1300 Celsius for 1 hour and flushed with nitrogen. And as you can see, there is darkening of the cubes. How many minutes do I have? I don't know.
No, 1 minute.
1 minute. Oh, hello. So yeah, this is what it gives. Here we have like the Chelyabinsk light lithology and dark lithology, where all the iron sulfides and iron nickel alloy have spread. And here we have the experimental runs with dunite, where all iron sulfides and have been spread as well. and forming at the same time some alloy. Very bright image. And so we came to the conclusion that actually this shock darkening is probably post-shock, meaning that we have one fragment from the impact collisions that flies and goes back into the asteroids within a melt, which is hotter. And this hotter melt will melt all the iron sulfide, will spread and darken the rock. And the next step that we are currently doing is that we have initiated some shock experiments to try to separate between shock darkening by heat and possible shock darkening by shock only. I will not explain too much now, but we have some spreading of melts. The problem is that tantalum has melted in this shock experiment as well, because we protected the sample with tantalum foil. And what I would like to do soon is trying to have the spectra down for these samples. But currently I'm working on other project with my colleagues, so it's something like I have all the time I want. And here are these work I've been doing.